All right, recording is rolling. So it is Friday, February 10th. So we're going to continue on these next time questions. Well, I'm calling next time questions for how to look with that title. This is part of the Paul Hewitt materials. So you guys remember yesterday, I played a bunch of Paul Hewitt demos related to things like thermodynamics, heat transfer, properties of matter, of materials. There was some stuff like Archimedes' principle thrown in there. And then we did a couple of these questions from this book. Oh, and before I get going too far, on Monday there's going to be a presenter from the Navy, so be nice to the presenter, to the guest. That'll be on Monday. So today we're just going to do these next 10 questions. Remember, we did 2 yesterday. We're going to do 10 today. Well, sort of 9, but this is a 2-parter, so 9 or 10 questions today. Okay. Actually, one of the ones we did yesterday, I would like to add more time to explain. So I'm going to take first few minutes to go through Archimedes' principle. So let's do a quick recap. The first one I did yesterday was if you scale up someone by 5%, say they grow like 5% taller, but it's also in 3 dimensions. Don't forget that. How much does the weight increase by? And if you take the 1.05 in 3 dimensions, your weight would increase by 16% actually. So someone who weighed 100 newtons will now weigh 116 newtons. That's a scaling idea. That's in the solids chapter. Okay. And then the one we did where like the bell ran out on us was we're looking at this floating block of wood. They're saying, what's the density of the wood compared to water? And the answer is, well, if it's floating, it must be less than that of water. But if it's mostly submerged, then it's greater than half the density of water. So the answer had to have been D, right? And there's this nice visual to show densities of different blocks of wood compared to water. So if it's the same density of water is greater than water, then it'll be like this, like it would just sink. Okay. Turns out if it's floating like half above, half below, it happens to have half the density. Now, I do want to prove that to you guys. I want to derive it using Archimedes' principle today, okay? And then the less density, it'll like float more and more. Okay, so this visual actually works out. The proportion that it's submerged is related to the ratio of the densities. So let me show you guys that is true before we do these other next 10 questions. Okay. So put all this to the side for a moment. So let's have a water line and something floating. It might be a block of wood. It might be an iceberg. Right? In the past, I've done like an iceberg version of this too, where part of whatever's floating is submerged, right? And part of it's above the water. Right? So right away, you know the density of the what's called a block of wood would have to be less than the density of water. Okay? Let's dive into this now. I'm going to set up a free body diagram for this block of wood, and I'm going to say there's 2 forces on it that are balancing each other out. It's got a weight acting down, so that'd be the mass of the wood block times the gravity field, right? And there's also what force is acting upward? What's it called? In this case, a buoyant force. Yeah, if it was like the there's a normal force holding that. But starting yesterday, we're going to call that a buoyant force. And Paul Hewitt was showing you guys. Remember, he took that weight and dumped it into the water, and he captured the water, and he showed that the buoyant force was equal to the weight of the displaced water. See how I hashed in part of this, just the submerged part? Like here, if you froze time and you pulled this block out, like, and then there was like a hole in the water, and you filled that hole with water, and you weighed the water that was in this submerged hole, right? The weight of that water is equal to this buoyant force, which is also equal to the weight of the block. Okay? So let me break this down a little bit more. There's a formula for a buoyant force, which goes like this. Density times gravity times volume. Okay? Now you have to know what density, gravity, volume we're talking about. This is the density of the surrounding water. So I'll throw around a subscript W for water, or really any fluid. Like if it's floating in oil, it would be the density of the oil. Right? If it's a balloon floating in the air, it would be the density of the surrounding air. G is the gravity field of the planet. Okay, and this V is specifically the displaced volume, not the volume of the entire block. No, that's too much volume. I'm talking about this hashed in volume right here. You guys know? And that right there is a different take on Archimedes' principle. Okay, that's what that is. Okay, so the buoyant force is equal to the density of surrounding fluid times the gravity field of the planet times the displaced volume. Okay, that is equivalent to the weight of the displaced water. Right, the water wants to fill that void. The weight of that displaced water is also equal to that. Okay. Okay. And I could do a similar idea for, I can make the weight of the wood also kind of match that format. Because do you guys know density? Rho is density, right? I think it's on a page I gave you guys a long time back. Is equal to mass per unit volume, right? We got mass per unit volume, right? Density is mass per unit volume, right? Could you rearrange that? Do a little side thought right here and say, well, the mass of something must be equal to its own density times its own volume. Would that be true? Mass is density times volume, right? And so what I'm going to do is I'm going to take that and substitute it in for the mass of the wood. I'm going to say the mass of the wood is the same thing as the density of the wood block times the volume of the entire wood block. Now that's not the displaced volume, that's the entire block. Right? Okay, so density times volume would be its own mass and then times G. Okay. Now, why did I do that? Why did I break apart this, which makes sense from last semester, into something a bit more granular? Okay. Because the fact that the forces zero out, you can say the sum of the forces in the y direction zeroes out, zero, right? That this minus this must be equal to zero. So then this is equal to this in terms of magnitude. So I got density of the water times gravity field times the volume displaced. That's Archimedes' principle right here. Has to be equal in magnitude to this right here. Density of the wood times the volume of the wood times the gravity field of the plane. Right? So is that okay? Sort of skipped a step. It should have said this minus this is equal to zero to satisfy that, but then it would just become that anyway, right? Okay. Do you guys see what cancels out on both sides? What cancels out? Gravity field of the planet, right? All that means, remember, connect this back to like some physical interpretation. That means that if you took this entire system to Mars and you had a block of wood floating in Mars, and it's like the same water and the same wood and what? Okay. The gravity field doesn't affect the answer, so it's still going to float the same proportion. Okay, so the ratio of the density is still going to be the ratio of like how much is submerged in the whole deal. Okay? But I'm about to prove that we're getting really close here. Okay, so what is this hatched volume compared to the entire volume? Right? Ooh, aren't those parts like here and here? The displaced volume is what's hatched in, and the entire volume of the wood is this right here. I'm asking what is that ratio? So I'm going to take this bit here, I'm going to divide it down here, kind of cross divide it. And I'll do the same thing with the density, but this would divide the other way. So the density of water gets divided over here. And it looks like this. The volume displayed, which is hashed in right here, divided by the volume of the wood. So I'm comparing those two. I'm saying, what is this compared to this? That's what that is right there. Is equal to the density of the wood divided by the density of the water. Right, this should be this is water right here, it's just specified. I didn't realize until I was like partway into this that wood and water both start with the letter W. Oops. Okay. But Archimedes' principle, we're talking about the surrounding fluid goes here. Okay, and then that all leads to this. Okay. So there you go. Right, that matches that picture in the book. Let's go back to that picture. Here it is. Okay. So that let's look at this one for example. Okay. So that if the wood had half the density of water, this would be a 1-to-2 ratio. Therefore, the amount displaced, the volume displaced compared to the volume of the entire block should also be a 1-to-2 ratio. That would match that right there. Right? You guys get that? So the same thing for both the 1-to-2 ratio. Matches that picture. Okay. There you go. So that involves a little bit of math but work, but wanted to prove that to you guys why that would be true. Okay, you guys get that? All right. Okay. All right, so next one we're going to do is number 19.2. We pull that up in the book. All right, 19.2. Compared to an empty ship, a ship loaded with a cargo full of styrofoam will float how? Lower or higher in the water? Okay, so we got a ship. We're looking at the water level on the side of the ship, right? Maybe like paint a mark on it. And then we're going to come along and dump a whole load of styrofoam into that ship. How's that ship now going to float? Lower or higher in the water? So on your paper, next to 19.2, write either higher or lower. And if you get it wrong, you just cross it out, write the right answer. When I pick this up from you guys at the end of the day today, all I'm looking for is that you guys were just following along. So if you have some wrong answers, you mark them out, then it's not going to dock points off you. All right, so everybody got a good guess, higher or lower? You guys ready for? I'm going to make my guess. I'm going to say that it's going to float lower because like it's the same ship, but now we're like adding weight to the ship, right? So it's kind of push it down further. Right? Even though the styrofoam in isolation floats really well, right? But if you're loading it onto a ship, all that's doing is like adding weight to the ship. So, right, answer: the ship loaded with styrofoam will float lower in the water. Right? Explanation: a ship will float highest when its weight is least. That is when it's empty. Loading any cargo will increase its weight and make it float lower in the water. Whether the cargo is a ton of styrofoam or a ton of iron, the water displacement will be the same. Ooh, right? Okay, you guys got that? Now this next one's a really tricky question you have to think really deeply about. So consider a boat that's loaded with scrap iron in a swimming pool. Right? I'm going to add a little bit of detail to this. Let's say the boat is relatively large and the swimming pool is relatively small. This is a swimming pool and not like a lake or something. Okay, so we're talking about a tiny swimming pool. The iron is then taken out of the boat and thrown overboard into the pool. Will the water level at the edge rise, fall, or remain unchanged? Hint, this is related to Archimedes' principle. Give you guys another hint too. If you think about a third scenario that wasn't mentioned, is what if the scrap iron is like over on the shore, right? Now you got three scenarios that you can compare. Right? So you got some scrap iron on the shore. You can throw it in the boat. That's going to do one thing to the water level on the side as it pushes the boat down to the water. Right? But if you take the scrap iron and like throw it down to the water, right? And now we're actually comparing. Well, the actual question is taking the scrap iron from the boat and just throwing it into the water.
Would it rise?
So whatever you think, put next to 19.3. So 19.3. Let me give you guys a little more time about that. All right. Well, I guess if I gave you a proper amount of time, it'd be like at least like 5 or 10 minutes. But I'm going to start to explain things. So does everybody have some answer written next to 19.3? Oh yeah. What do you think?
I said the water level would lower.
So you said it would lower. What made you think it was going to lower?
Because if there's a lot of metal in it, then the ship will like sink lower, so it will displace the water, and the water level would go up. So if you remove the weight, then the ship would go back up and be less water displaced, and level would go down.
Yeah. Okay. I wasn't sure if you guys were going to get this, but Evan cracked it. Yeah. The water level will actually fall. Right. So we tried to recap what Evan was saying, and then we'll flip over and look at their explanation. So again, let's take some deep thinking. So hopefully one of these explanations is going to flip. Okay. So let me start with the iron over on the shore, which they didn't really mention, but right. And then you put the iron in the boat. Well, that's going to press the boat down, and it's going to raise the water level itself, right? That action. Okay. Now, how much does it press the boat down? Like how much water does it displace? Well, that kicks back to Archimedes' principle. Remember, Archimedes' principle says that the amount of water that it displaces is equal to. Hold on, I go back. Right. If you put a weight in there, then it will displace a volume equal to the weight of the water displaced. Right. So if you have like a lump of iron, like this right here, is extremely dense and very heavy. So guys, what would an equivalent weight of water be for this 1 kilogram mass? It would be larger in volume than this, wouldn't it? Right. So let me like draw this out. So this is still an Archimedes principle situation. Okay. Here is like 1 kilogram of iron. 1 kilogram of iron. Here is 1 kilogram of water. Those could both be 1 kilogram, right? Right? I'm exaggerating a little bit, but you guys get the idea. So if you take 1 kilogram of iron and put it into a boat, that boat is going to press down and displace this much water, which is a bunch of water. Then when you take that kilogram of iron out of the boat and throw it directly into the water, sure, it displaces some water, but only this much, which is not as much. Therefore, the water level is going to fall. Okay. All right. So here, let's see exactly what they say. Again, this is one you have to like see a few times and think a few times. Okay. Here's all 3 scenarios. Here's the iron over on the shore. Here's the iron in the boat, which displaces the most water. And here's the iron submerged, which displaces some water, but not as much as when it was in the boat because of Archimedes' principle. Okay. So the water level inside of the pool will fall. Yep, that was the correct answer, fall. Because the iron will displace water, but less water submerged than when it was in the boat, when it was floating in the boat, right? So remember, it was in the boat, it displaces a volume of water equal to its own weight, which is a bunch. Right? But when it's submerged, say when it's down at the bottom of the pool, it only displaces an amount equal to its own volume, which is not as much, less. Okay. Guys got it? Okay, next one, 1904. 1904. A fire truck carrying a load of firefighters, a large tank of water, is about to cross a bridge that may or may not support the load. So there's like some maximum capacity saying, oh, what have we got on board? And it's like pretty much that number, like, ooh, okay, so this seems kind of dangerous. The chief suggests, hey, maybe some of the people should climb into this tank of water and just like float. Ooh, because I know when I'm floating, it feels like you have less weight, right? So is this a good idea or a poor idea? So next to 1904, right, either good or poor. How about that? It's a good idea or a poor idea. I guess the more physics way to think that would correspond to is if those guys crawl into the tank of water, is that going to alleviate force from the bridge and make it less likely that the bridge is going to collapse? Good idea or poor idea? All right, everybody got an answer next to 1904? 1904? What do you guys say? Good idea or poor idea? Good call. Poor idea. All right. Because that doesn't actually change anybody's weight, does it? Right. What it would do is like alleviate their apparent weight within themselves, but all that would do is it would increase the pressure on the bottom of the pool because they would like be displacing some water. So the net effect would be like no change. It's still going to be the same weight, the exact same weight on the bridge. So answer, this is a poor idea because the weight of the load doesn't change when people float in the water tank. The load the bridge supports will still be the weight of everything, right? So the truck, the people, the tank of water, it's the same, right? I've seen a variation on this question that involves, here, I'm gonna change the story a little bit, but it ends up being the same result. What if there was a guy driving a truck full of bird cages and birds? Right? You got a bunch of birds sitting in the bird cages, just like taking a snooze. Okay? He's about to go into a weigh station. He's like, I think I'm a little bit over the weight limit. Ugh. Hey, I know what I can do. I can go back to the back and like go and get all these birds like flying around. When they're flying around, they're not perched on the bird cages, and maybe that will alleviate some of the weight. But it's the same result, and which is that it's going to make no difference because when those birds like flappen their wings down, they have a downward pressure which holds up their weight, and that downward pressure transfers to the bottom of the truck, which is still going to register in the weigh station. So that would make no difference. Okay, so similar idea. Okay, 1905. Okay, now this one's a two-parter. So 1905. Okay, you guys got a couple spaces for 1905? Okay. A block of balsa wood. Yeah, a block of balsa wood with a rock tied to it is floating in the water. Now, see how you have the rock tied to the top of the balsa wood. You guys know balsa wood, it's like really low density wood. You might find it in like craft stores. When the rock is on top, as shown in this figure, exactly half of the block itself is below the water line, like this picture. You guys see like half and half of the block itself. When the block is turned over, so that the rock is underneath and submerged. So we're gonna take this whole thing and flip it upside down. Now, the amount of the block that is below the water line is what? Less than half, half, or more than half. Right? And there's also a follow-up question. What happens to the water level at the side of the container? Does that rise, fall, or remain unchanged? So give you guys a minute to think about that. All right, I guess ideally I'd give you more time, but okay, got some time constraints. So, what do you guys say for the first question? What do you guys think? Here, let me see show of hands. How many guys said less than half? Option A, less than half. Okay, yeah. All right. So actually, if you said that one, that's the correct answer. Right. I'll flip it to an explanation. How about this? The follow-up question, the water level on the side, kind of an independent question, sort of. How many guys said the water level would rise by turning upside down? How many guys said it would fall by turning upside down? How many guys say it would remain unchanged by turning upside down? Oh, yeah, double winner. So the answers are A and F. Okay, A and F. Okay. Again, if you missed those, just cross out, write the right answer. That's right. Okay. Right. So, why is it A and F? When the rock is on top, the whole weight pushes the wood into water, but when the rock is submerged, the buoyancy on it reduces its effective weight and becomes less than half the block is full beneath the water line. I don't know. I don't really resonate with that explanation, but there's another explanation I have, which I think makes more sense. Or by the law of flotation. So I think Archimedes' principle. The rock and wood unit, like collectively, displaces its combined weight, right? Remember Archimedes' principle. The buoyant force is equal to the weight of water displaced, right? Which is not going to change, right? And the same volume of water, whether the rock is on top or the bottom. Therefore, when the rock is on the bottom, now the rock itself is displacing more water than it was when it was in air. So not as much wood is going to be displaced. So less wood is actually beneath the water line. Okay, so that takes some thinking. Right? Right. And then how about the follow-up? So why does the water level remain unchanged? Right. Well, I mean, it's the same weight down, it's the same buoyant force up. It's so it says since the same volume of water is displaced no matter how it flows. I mean, that's also true, right? The same volume displacement. The water level of the side also remains unchanged. Right. So it doesn't matter how it's oriented, it displaces the same volume of water. Okay, guys good? Right. 20-1. 20-1. Compared to the mass of a dozen eggs, the mass of an air in an quote unquote empty refrigerator is. So you open up the fridge and say, hey, it's empty. Wait a minute, it's got air. Oh, wait, there's also a dozen eggs in there. So what has more mass? Oh, yeah, good. Actually, here. How do they word this? Compared to a dozen eggs, the mass of air is what? You might remember this one from yesterday. Those Paul Hewitt demos. He actually told you guys the answer there. Right? And did you guys say it was actually C or D is both good options. Let's run through the numbers. So cubic meter of air at 0 degrees Celsius, maybe it's so fridge temperature is probably a little bit above that actually, because we're not exactly freezing things. But and normal atmospheric pressure has a mass of about 1.3 kilograms. Now that's 1 cubic meter. Now, a medium-sized fridge is maybe let's call it 0.6 cubic meters. So multiply those together, about 0.8 kilograms of air. I mean, it depends on the size of your fridge, I guess, right? But dozen eggs, 0.75 kilograms, those are about the same. These numbers exactly, if you like, you could have also said D. So C or D would both be good options. So you said C or D, either of those would be good options. Okay. I like this follow-up too. We don't notice the weight of air because we are submerged in air. If someone handed you a bag of water while you were submerged in water, you wouldn't notice its weight either. True. Swimming around the pool. So it says here's a bag of water. Right? How much does it weigh? Well, it would feel weightless, right? It might have some inertia, but wouldn't have any up or down weight because the buoyant force would cancel out. Right? Same thing if I hand you a bag of air right now. Right? But you guys see that helium balloon over there in the corner? That's like floating to the top. That is some evidence that air around has some weight, right? Because the helium balloon has less weight, so it's less dense. So it's gonna, I should say it's less dense, right? Kind of float. 20-2. Consider an air-filled balloon weighted so that is just on the verge of sinking, right? So it's floating, but just barely, right? And okay, so its overall density is pretty close to that of water. Maybe it's like 0.99 kilogram per cubic meter or something. Now we're going to push it beneath the surface. So you're going to push about a meter down. What's it going to do? Got three options there. Give you guys a hint here. The fact that it's a balloon matters. See, if it was just like a block of wood that was barely floating and you pushed it down, the answer would have been that it would return to the surface, which would have been option B. But the fact that it's a balloon, something else you got to keep in mind. You guys remember ideal gas law? P V equals nRT. Ideal gas law. Right? So we're pushing this balloon down. Okay. Let's say the temperature is pretty constant. The number of air molecules of the gas doesn't change, and R is just a constant cell. So all the stuff we're just going to treat as constant, pretty close to it, right? But if you're pushing it down, guess what's happening to the pressure the further down you go? It's increasing the pressure. That's actually a direct relationship. If you push it 3 times further down, that's going to triple the pressure. Well, just from the water anyway. Okay. And if the pressure's going up, what's happening to the volume of the balloon? Going down. Inverse relationship, right? Okay. So for example, here. 3 units times 8 units is 24 units. If you increase the pressure, let's say you double the pressure to 6 units. Now the volume gets half, so that it comes out the same constant value, just for example. Okay. All right. Since the volume is less, what's the overall density of the system? Density is mass per unit volume. Same mass. Smaller volume, what's the density? It's bigger. It's greater. This is greater density than this because the balloon is smaller. So what's it actually going to do? Sink. It's going to sink. Oh, and here it is here. The balloon will sink. So as it goes down, gets squeezed in, ideal gas law. So its density goes up. And if it was just barely float before, now it's gone. It's going to sink all the way to the bottom. Right. Okay. 20-3. Birthday candle burns in a drinking glass, right? Just like this picture. Right, and we're going to whirl this around in a circular path. So take it around this way here, just here. So I'm here, just going around a circle like this, right? Now, so it's kind of like a centrifuge type setup, right? Like a centrifuge going around. What will the flame? Which direction will the flame point? Okay, which direction will the flame point? Outwards or inwards? Okay. Give you guys a hint. Right. Got this Smarter Everyday YouTube channel, just a bunch of science stuff. Right. Goes in his car, and do you guys see the pendulum hanging from the ceiling? Right. He steps on the gas,
See how it swings backwards? Now, really what's going on is the pendulum has a bunch of inertia, wants to sit there. The entire car moves forward. So relative to the car, the pendulum wants to swing backwards when it accelerates forward, right? So, right, you step on the gas pedal, you feel like you're thrown back into your seat, right? Then, fast forward a little bit, helium balloon. Now, guys, what has more density, that helium balloon or the surrounding air? Surrounding air is more dense. So when he steps on the gas pedal, what's going to happen? It's going to go forward. It's going to go forward. Moment of truth. It does go forward. And when he slams on the brake, it goes backward, which is like opposite of like how you feel in your seat. Ooh. Okay. So let's go back over to this candle flame. Guys, what's more dense? The candle flame or the surrounding air? Surrounding air. Right? Say I also threw a marble in there, right? If you go around centrifuge, the marble's going to go to the outside. All the dense stuff goes to the outside. So which way does the candle point? Yeah, inward. Right? Inward. Okay. Here we go. Okay. So, I like this diagram because see all those dots? Those are like dense air molecules, right? Relative to that candle flame. Okay. So centrifuge, all the dense stuff goes to the outside, all the less dense stuff towards the inside, including the candle flame. Try that too. Okay. Guys good? Okay. This next one, well, here, we're gonna sort of skip this one. I'll do this real fast. So inside of an oven at 200 degrees Celsius, woo, touch that, you're gonna burn yourself. But we got this 1200 degrees Celsius sparkler. If you're hit by one of the sparks, you're usually okay, as long as it doesn't hit you straight in the eye. So why? So explanation is the temperature is like energy per molecule, right? And when you're touching an oven, you're touching lots of molecules, so that's lots of energy. But a little sparkler has hardly any mass at all. Right? We're talking about little tiny sparks, right? So even though it's large energy per unit mass, it's hardly any mass, therefore hardly any energy. Okay, we're gonna skip hit straight. Talk about 21-2. I got a piece of iron, 10 degrees Celsius. We're gonna double the temperature. What is the doubling the temperature? Guys, can you is it 20 degrees Celsius? You have to convert to what first? Kelvin. So temperature Kelvin is equal to temperature Celsius plus 273. So wouldn't that be 10 plus 273 is 283 Kelvin, right? Times 2 is 566 Kelvin. Right, so that's doubling the temperature right there. If you double temperatures, you have to do it in Kelvin. You can convert back to Celsius. Subtract 273. That's 293 degrees Celsius. So 10 degrees Celsius. If you double the temperature, it's actually 293 degrees Celsius. Right? Because you have to go through Kelvin first. Right? Fahrenheit and Celsius are just relative systems. So if you want to scale something up or down, gotta be Kelvin. There you go. And then there's the explanation there. I'm trying to go on. Okay, last one. We're gonna do one more and then I'll turn it in. One more. Iron ring. You heat it up. Of course, the iron itself expands, but what about the hole in the middle? Is the hole in the middle bigger or smaller? Also bigger. Remember Paul Hewitt did this one yesterday? You guys remember that? Okay. So we got 293 degrees Celsius or 566 Kelvin. Right, and then the hole itself is larger. All right, so turn this into the gray tray, and as long as you got those right down, then I will give you guys some points for doing that. There you go. That is a wrap on this week. Oh, you guys remember Navy presenter on Monday, so be good for our Navy presenter guest on Monday. All right, you guys have a great weekend.